Now, in the first part of the lecture, we consider the motor as a molecular machine that is really working in real space. Yet, what we also saw is that the motor needs energy. And the discussion that we are going to take in the second part is how there is a coupling between the chemical energy and the working of a motor. And we will describe the motor just as an enzyme that facilitates the chemical reaction from ATP to ADP. Now, the most important take-home message of today's lecture will be that the description of whether we describe the motor as a linear machine in real space or an enzyme that actually we will see will walk in the energy landscape is exactly the same and leading to the same results. Okay, so in the first part, we looked on the real space movement of motors, and we found that the speed of the motor is force dependent, and we could calculate even the velocity dependence of that motor. So what we neglected in our description is what actually happens at the border of the box where the energy is released. Hence, how is the coupling between the mechanical movement of the motor and the chemical reaction that is taking place? What we are after is that we look again back into experimental data, and we find that the velocity also depends on the ATP concentration, so the fuel concentration that the motor has available. Maybe here already I want to point you to the fact that there's a maximum velocity that the motor can walk, where the maximum speed is also dictated by the concentration of the ATP. And there is some, at very low ATP concentration, the motor considerably slows down. Now, the motor we're mostly concerned with, as an example here in the lecture, is that of kinesin. This is a motor that is carrying vesicles on microtubules. The mechanical cycle is displayed over here. So we start out from motors just floating in the solution, and you have the microtubules, which are actually polar polymers. So there's a difference between a movement to the right and a movement to the left. Now, in solution, the kinesins come as ADP-loaded motors. So there's no energy in those molecules. Yet if they are ADP-loaded, there's a high probability that the motors and the feet of the motors will bind to microtubules. So that you see in the first step. So in the first step, there's a 1 foot bond. Now what will happen is there's an enzymatic reaction going on, and the ADP will leave and the ATP will bind. That will make a strong binding of 1 foot of the motor to the microtubule. The second foot, which is ADP loaded, is now freely to wiggle around this 1 foot which has been bound. It can go backward, it can go forward, and that is a very fast movement that we described as a diffusive motion. Now, by chance, also the second foot can land on the microtubules. Then, fastly releasing ADP, hence this motor will get stuck on the microtubule. The distance between the 2 feet is 8 nanometer, just dictated by the shape of the rail, which is the microtubules. Now in the next step, the ATP of the back side of the motor will be transferred into ADP, thereby a phosphate is released and energy is produced. In this case, the back foot is ADP loaded and can release from the microtubule, where the front foot is firmly attached to the microtubule. And it's exactly that moment of the release of the phosphate that energy is released, and the motor applies a force to its load and makes a step forward. So let's take a chemical view of molecular motors. So the working of the motors in a chemical sense is to speed up the reaction from ATP to ADP. Hence, they're described as enzymes. Enzymes are a type of catalyst that speed up reactions without being changed by themselves. Now, if we write down a chemical equation to catch this idea, we start out with an enzyme plus a substrate, which is ATP in that case, leading to a bound substrate to the enzyme ES, which in turn will catalyze the reaction, leading to an enzyme loaded with a product P, and finally leading to an enzyme plus a product. Now in our example, the enzyme would be the kinesin motor, the substrate would be ATP, and the product would be ADP plus inorganic phosphate. In terms of the free energy, the reaction will follow the path along a reaction coordinate. So that's a picture that you have been discussing in Physics of Life 1. Now just showing here some buffaloes which are running along a plane and just fall into a trap. The y-coordinate in the system is the energy, the free energy, G, of the system. So we start out at a high energy in one state, S2, and fall down into a low energy state, S1. Yet typical for such kind of chemical reactions is that there's some activation energy needed. There's a little hill before or in front of the cliff before the energy is completely released. And the chemical reaction first has to overcome this little hill, which is called the activation energy, delta G dagger dagger. Sometimes in chemical literature you also will find that delta G dagger dagger is called delta delta G. So just to summarize our ideas here, so if we have a spontaneous reaction, the spontaneous reaction is slowed by this activation barrier, delta G dagger dagger, which we actually also can split into an enthalpic and an entropic part, delta E dagger dagger minus T delta S dagger dagger. Now the working of the enzyme actually is to reduce this activation barrier, hence speeding up the transition. That is displayed on the bottom graph. So we start out at the top with a regular activation barrier for a chemical reaction. Now by binding of the enzyme, the activation barrier is reduced. Now we have to realize that the enzyme is actually a cycling machine. Hence, this one activation barrier that we just described is repetitive. Hence, we can construct a 1D energy landscape that will roughly look like this. We have a stepwise motion, but before each step, there's a little bump in the free energy. Now, just comparing to the energy landscape that we had for the real space motor. Here, it looks very similar. Here we had, again, also a rising energy landscape before the final step is coming, and this increase in the energy right before the step is given by F times L. Hence, what we could identify is that the delta G dagger is equivalent to F times L of the real space machine. Likewise, the delta G in the case of the enzyme, which can be split in delta E minus T delta S, we can identify with the energy jump of the pranks epsilon minus F times L in the real space machine. It's also worth considering what is driving the delta G in this case. Well, if we go back to our discussion on, actually in the first lecture, where we saw that delta G is mainly given by the availability of substances or the log of the concentration of the substance, we see that the delta G in the case of considering the concentration of, we see that by the chemical reaction where we reduce the concentration of the ATP, so the substrate, we see that delta S is negative in that case, and that means the process is driven by entropy of the substrate. This is reversed for the product. During the reaction, we add more product. In that case, delta S in terms of the product is positive, and the delta G will be reduced. Now let's put all these ideas together. We saw that the enzyme motor can be viewed as a motor that is walking in energy landscape. Now the energy is given by delta G equals to delta E minus T delta S, which equals to delta E, so the amount of energy in the chemical reaction, minus kBT times the log of the concentration of the substrate. Now this delta G we can identify with the F times L in the thermal ratchet real space model. Hence, using this identification, we easily can obtain the speed of the enzyme. If we just identify F times L with delta G. And by doing so, we see that the speed of the enzyme is given by some prefactor, which we call Vmax, times e to the power delta E divided by kBt times 1 divided by C plus delta G divided by kBt minus 1. Or rewriting, the speed of the enzyme V is equal to Vmax times the concentration of the substrate divided by e to the power delta E divided by kBt minus the concentration times delta G divided by kBt plus 1. Now, this form of the curve is exactly following the experimental data. So here I show the velocity of the enzyme as a function of the concentration of ATP. So you see at very low concentrations the motor is very slow. At high concentrations the motor is fast. We could have also obtained a very similar solution using a pure chemical approach. In the chemical approach, we consider an enzyme and a substrate at given concentrations. Now, in the first step, the enzyme will bind to the substrate. Then we saw the working of the enzyme is that while binding, the chemical reaction is coming forward and the enzyme will bind to a product, which finally leads to the release of the product. Now, this complicated and multi-step process we can even shorten because the very last step, the release of the product, typically is very fast. Hence, we only come up with two chemical reactions. We start with ES, then we have the bound state ES, finally leading to the free enzyme and the free product. Now, to all of those steps, we can assign rates. The first forward rate from E plus S to ES is given by the substrate concentration times K1. There's a backward process that also can happen. So the enzyme releases again the substrate, nothing happens, which we call K minus 1. And finally, the final step, where the substrate is turned into the product and the product is released from the enzyme, characterized by a rate constant K2. Now what we could look for is what is the change in occupation, so bound substrate of the enzyme. The change in probability that I have a free enzyme, PE, is then given by minus K1 times Ks times 1 minus the probability that the enzyme has bound a substrate, ES, plus K minus 1 plus K2 times the probability that the enzyme has bound a substrate. Now, in steady state, this derivative has to be 0. So we simply can now solve for the probability PES that the enzyme has bound a substrate, and we come to the solution that this is given by K1 times the concentration of the substrate divided by K1 times the substrate plus K minus 1 plus K2, which typically is summarized into the Michaelis-Menten equation is given by concentration of the substrate divided by concentration of the substrate plus Km, where Km is the Michaelis-Menten constant, K minus 1 plus K2 divided by K1. From here again we can calculate the speed of the reaction, where the speed of the reaction is given by the concentration of the enzyme times K2 times Cs divided by Cs plus Km, or reformulating this, that the speed of the enzyme is equal to maximum speed, V max, times Cs divided by Cs plus Michaelis-Menten constant Km. That's the so-called Michaelis-Menten rule. And we have seen earlier that the Michaelis-Menten rule nicely describes data taken on the kinesin motor. Now we also can reformulate the Michaelis-Menten rule by calculating 1 divided by the velocity, which then is equal to 1 divided by Vmax times 1 plus Km divided by Ks. So if we now plot 1 divided by v as a function of 1 divided by the concentration, we get a linear relationship, and that is called the Lineweaver-Burki plot, where from the slope we derive the Michaelis-Menten constant, and from the crossing with the y-axis we obtain the speed of the motor. So let's wrap up what we learned about the kinesin motors and molecular machines and molecular ratchets. So we started with experimental results and an experiment where people have looked on the mobility of individual kinesin motors. So these motors are small machines of a size of maybe 20 nanometer, where the machine is walking on a rail that has a certain polarity. Now the experiments showed that the movement of the motor is a stepwise motion. The steps taken is 8 nanometers, and between steps there's some weighting. Now the weighting can be described by some diffusional motion of one of the feet of the motor. Now the experimental findings further show that the speed of the motor depends on the load. Now what we did is we developed a model to describe this, and that is a model based on a thermal ratchet that is working against a load, yet has an energy source that results from the burning of ATP. And by using this model, we could, for example, describe how the speed changes with load. Now in the next step, what we looked in and we viewed the molecular motor as an enzyme. Again, for enzymes, it's found that the speed of enzymes depends also on the availability of fuel. Again, what we saw is that we could explain the enzyme as a molecular machine that is walking in the energy landscape given by the chemical reaction. And by doing so, we found that we could explain also the speed versus fuel dependence that experimentally has been found. Now it's now roughly 10 years ago that actually a molecular motor has been viewed and followed in real time using atomic force microscopy. In this iconic experiment by Toshio Ando, you really see the motor walking on a microtubule, and you see that it's walking hand over hand, as it's called, where the second hand is displaying a diffusive motion before it finally binds and the motor can make a step. Now, this stepping motion is not a single observation just for kinesin. Actually, there have been even more sophisticated experiments done on kinesin, where where people even have identified substeps of the motion, which refer to changes and binding of, for example, the second feet to the microtubule. Yet, what I said is these motors are not only the molecular motors that transport vesicles, but, for example, the similar experiments have been done on RNA polymerase, which again is a molecular motor walking on DNA. And for that particular enzyme, steps as small as 3 angstrom have been identified as the RNA polymerase walks from base to base and producing a replicate of the DNA. So in summary, the take-home messages for lecture 5 is that we looked on molecular machines and we identified that molecular machines can be described in two ways in an identical way. On one hand, we can view the molecular machine, in that particular case the molecular motor, as a machine working in real space, or we can describe it as an enzyme that facilitates a chemical reaction. For both, we developed a model where we could identify real work done on a system in the real space model, whereas in the enzyme model, this is a walk of a molecular machine in a complex energy landscape. We found that the machines have a maximum speed. Molecularly, we found that the speed is given by diffusion. In terms of enzymes, we derived the equation for the Michaelis-Menten kinetics that describes the speed of an enzyme given by the speed is equal to Vmax times concentration of the substrate divided by the concentration of the substrate plus Km, where Km is the Michaelis-Menten constant.